Hello, our group is SIGNIT, Sign Language Interpretation Network and Information Transcription. Our group initially sought out to check the feasibility of a sign language application in the real world. From this dataset, we drew a few visual conclusions that would lead us to believe that it would in fact be applicable. The most prominent one, average hearing loss is increasing year by year. The majority of our data manipulation was done on an ASHA report provided by the Government of Canada, and further visualization and data analyses that did not fit in the 5 pages of our report can be found in a separate link that we've provided. In the increasingly digitalized age, those that are deaf or hard of hearing find it difficult to fit in with the rest of the population. We wanted to develop a solution, so those of us that have not learned sign language can communicate with various family or friends that do majorly use it across the digital sea. To accomplish this goal, we needed our application to be robust and scalable, along with easily accessible and convenient. Should you engage in a video call with your family or friends, we wanted that application to be able to translate in real time. And if you wanted to watch a video that they've sent over, we also wanted our application to be able to decipher that. And indeed, our application accomplishes all three. Okay, let's go over the code demo. So after running.md, you should end up with the main menu. This takes in a URL, this takes in a folder, this takes in a video. Let's do the folder for now. I prepared a folder that says hello world in sign language. We'll put that in and out pops our window that's running our Spark program. We'll resize this and keep this around while I go over the ETL process and the main pipeline. So we got our data at first from Sign Language MNIST, but we wanted a bigger one, and a bigger one we got 1.11 gigs zipped, by the way, because every single folder had 3,000 images in it. And obviously we can't use raw JPEG, so we had to do some ETL process somehow, and that's right over here in dataset creation. Firstly, we picked every 5th file as our training set and every 250th file as our testing set, filtered out all the duplicates, and then ran SIGNIT convert on data mode. SIGNIT convert on data mode takes in the files as binary files into an RDD, maps them so they're the correct size, maps them again so they're the correct formats, and writes them to CSV. And after that, we ended up with folders and folders of CSV, each of them 100 megabytes each for every single letter. Massive, I know. Anyway, let's go over the pipeline, which is also in SIGNIT convert. Firstly, takes in any image. Secondly, identifies the hands. Thirdly, crops around the hands, and after that resizes it to 100 by 100 in grayscale, and then finally outputs a letter in output.txt right over here, or the final sentence. Now, because of the demo, this is let me just show you what the CSV looks like. One row, 10,000 or so columns, and then if we convert it back using CSV to image, we get up with this thing. Now, I usually have intermediates turned off, but because of the demo, I'll turn them on, and we see the intermediates are in fact what we expect them to be. And let's take a look closely at SIGNIT convert and its scalability. We see that not only is the main code scalable using all PySpark, but also that the ETL process is also scalable because we wanted both modes to be scalable because this is a lot of data. Now, we see that the Spark program has finished, and it is in fact written another line to output.txt, and that is not hello world, but we'll go over why that is in a second. For now, let's close this. I said let's close this window, and that gets us back to the main menu. Now let's run the video, and I prepared a short video, 3 seconds of me holding my hands up in what appears to be a W. We'll enter that in here, and how this differs from the folder images is basically first it chops it up into frames, selecting like 2 for every second or so, and then it runs the convert again on these frames. Since this is much of the same thing, I'll see you when this program is done running. We are back again, and we see it has output to N and VVV. Not exactly W, but V is pretty close. And we take a look at the intermediates. Yes, in fact, it has what we're looking for, and resize it around the hands, and that corresponds to our 5 video frames. All right, let's return to the main menu, and now we want to do SIGNIT Stream. However, SIGNIT Stream requires me to set up a live stream, so I will see you in. And we are back. We have our lovely live stream open over here. We'll take that URL, and we'll post that into SIGNIT. And the name of the stream, mine. And we'll see that our Spark program is open on this window over here, but our live stream to frame program is actually open on main over here. This is just to show you evidence it runs. We'll see you in 60 seconds. And our PySpark program has finished along with our frame ripper down here. Note, we did have to switch to a YouTube live stream because YouTube supports our intermediates a lot better. However, please note this program works with all live streaming services that FFmpeg can rip off of, not just YouTube. Now, speaking of intermediates, here are the intermediates from that live stream where I was working on code. As you can see, checks out with what we have. These get processed into a parquet file, more on those later, and afterwards these are the representations of the data frames that go into the model itself. We can take a look, see if these CSVs lined up with the images that we have, and indeed we do. This matches up quite nicely with what we have over here. Now, notice there are 5 of them. That's because every single CSV has 5 of these images. Why is that? Well, that is because our FFmpeg command in stream input.py reads 5 frames per second from the live stream. Afterwards, it takes those 5 frames and then centers it around the hand, formats it, and then saves it as a parquet file. We can adjust these number of frames up or down depending on your preference. Now, please note that stream input.py is not a PySpark file. The reason for this is 2.5-fold. Number 1, FFmpeg is really fast and catches up to live streaming pretty much simultaneously. And since one person can only watch one live stream at a time, or the most common person at least, it should work completely fine, even at a higher scale. However, our stream input.py does actually run multiple streams at once if you wanted it. Here is it in action. And if we just wait a little bit, here we go. As you can see in the intermediates, this one is from Al Jazeera, and this one is from the relaxing music stream. If I can just get, yeah, there we go. Number 2, PySpark streaming in particular has very poor support for reading images. The only way you could do that is with binary records stream. However, this requires a record length, basically how many bytes you're going to read. And with streaming of varying quality, we found it more practical just to offload it to stream input.py. Number 2.5, we did try other methods, as in saving the pre-processed image as a text file rather than an image file, so you can read it with PySpark streaming text. However, this is the text file that you end up with, and PySpark does really not like this file. Now, you can actually convert it back to its original image with a custom Python file, like so. However, the moment you try to read this in with PySpark, it will throw null errors at you. It will throw type errors at you. It will throw all the errors at you and just refuse to read it. Trust me, I've tried. So this is what we're left with, and it works quite well. No complaints. Now, with SIGNIT Stream, it has the easy task of monitoring this folder for parquet files, and afterwards it just loads those parquet files in as a data frame over here, and then just applies the model on the parquet files. Now, because there are 5 files for every timestamp, what we can do to make our model just slightly better is we can aggregate on the timestamp and get the most common letter. That way it has 5 chances of getting it right, or at least we hope. This is what we finally output. You will not see this. This is just an intermediary, and you will just see these final signed letter for every single second. This is our classifier. We're using TensorFlow Keras sequentially with convolutional hidden layers running for 30 or so epochs and giving us these loss curves and these accuracy curves. Now, the question becomes, why is our predictions not that great when our accuracy curves look like this? 2 answers. Number 1, image recognition is a hard problem to solve. So hard, in fact, Google 7 months ago put out a $100,000 prize, and we did not win that, unfortunately. Answer number 2, this is trained on MNIST, 28 by 28, and this one over here is trained on only a subset of our ASL library, namely 350 or so images versus our massive 84,000 that we have in total. And now the question becomes, well, why didn't we use PySpark MLP for that? Because we have such big data. And the answer to that is we did. We did try, in fact. However, if you'll notice, PySpark doesn't actually have a CNN classifier at all. So we tried using random forest. We get an accuracy of 56% on the MNIST, by the way, not even the ASL library. And on the MLP model, we get a whopping 18% accuracy. So I hope that answers the question. So in the end, our large model that was trained on 350 or so testing images, 5,000 or so training, and 2,000 or so validation ends up with a final classification report of 42% accuracy. Not that bad considering that there's 28 labels. In summary, our project set out to bridge the divide between the deaf and the able. We were working with a lot of image data and needed to make that work with Spark despite the two being largely incompatible. We chose PySpark because we want the main application to be scalable, FFmpeg because it is fast, and TensorFlow for the access to convolutional hidden layers. We have had a lot of problems, but we ended up with a proof of concept application that is somewhat competent but needs improvement in a critical area to be truly impressive. I hope you've enjoyed this video. Remember to like and subscribe, and I will see you guys next time. Bye-bye.